It gives me great pleasure to turn this event over to our discussion leader, Brian Christ from Agilent Technologies, who will introduce the panel for today's topic. Go ahead, Brian.
Hey, thanks very much, Madison. Welcome, everybody. We have another quarterly meeting of the DDG online meeting, and we're very fortunate to have my colleague Ken Boda and a longtime associate, Vivian Gray. And we're going to talk today about dissolution sink conditions. To handle sink, we'll go through this, and then how, one of the most common ways we see in dissolution methods is to possibly during development add some type of surfactant. Sometimes we increase volume, but other ways, surfactants are very common in dissolution testing, in fact recommended by FDA, to allow us to use standardized, dissolution volumes and equipment and so forth. So we'll talk about these as we go through. So again, we welcome you. If this is your first time here, welcome. We're glad you joined us. And for people that have been here in the past, welcome back. We're glad that we can continue to provide this forum. It's sponsored by Agilent. But the DDG is a fairly independent group. It's a bulletin board, and we have a lot of interaction on that bulletin board for, problems that face dissolution chemists all over the world. But this DDG online meeting started some years ago. We're in our 9th year now, and we're up to 30. This is our 35th session, and Ken has been with me through just about, I think, every one of them, Vivian on many of these. So we hope this provides some good information about where you can turn to find maybe some solutions on your dissolution method development and validation activities. So this is a free online interactive bulletin board that's associated with this. If you've been there or not, it's just very simple, going to dissolution.com, and you'll be able to be directed to that site and the bulletin board and any messages like these meetings as they upcome, and I'll place to register for them as well. So our mission is really to provide, a discussion forum for practical issues that affect pharmaceutical chemists that are generally developing, validating, and performing routine dissolution tests. This does spill over into the related chemical analysis sometimes because of low concentration or high concentration, it affects how we do a dissolution test. So we go into, quite a few avenues to, to provide a good forum for dissolution discussion. The home page you'll see here, this is actually showing the meeting topic of today, sink conditions and surfactant level justification. And we hope you join us for our next meeting as well, which is November 14th. And this is arising for, a lot of need for testing of micro and nanoparticles. So we're going to discuss some drug release testing techniques for these two types of dosage forms. So we hope you tune in then as well. It's a little bit hard to see probably all the meetings that we've had, and you can go to the site and you'll see all of these meetings listed, and in fact they're all recorded. So if there's something here that you'd like to go back and look at, or just to get a little bit of information on, we try to keep these topics contemporary. You'll see a lot of things maybe where there's a new USP chapter introduced, we'll discuss. But sometimes we have to get back to some basics like today's topic, surfactant justification, because it's been around quite a long time. And, even though we've touched on it in previous episodes back in 2014 and another in 2017 on solubility, this sort of ties some of those together. So hopefully you'll find some benefit from this. So again, myself, Brian Christ with Agilent, Kim Boda, my associate, he's also from Agilent. Vivian used to be with USP long ago. She's the editor of Dissolution Technologies, and of course, she runs VA Grade Consulting. So she's quite a busy person. So we're really glad that she found the time to be with us today. She's been very she's joined us for quite a few meetings. She's participated. We really appreciate that.
Sure thing, Brian. It's good to be here.
Oh, all right. So the objectives today, you know, this is a fairly informal discussion group, and what we do is we focus on some certain areas. For instance, today we're going to look at sink conditions, and this is based primarily on, you know, what we have to deal with Class 2 and 4 drugs, the poorly soluble drugs. So that leads us right to discussion on solubility determination. There's been recent USP chapter introduced after years of, you know, finalizing that chapter. We'll also talk about solubility-related issues. And then, of course, to deal with that, there's a number of ways you can do things to increase solubility. But, again, one of the most common is surfactants, but these have to be justified. So we'll spend some time there. Now, your participation is very helpful. Sometimes it may not be a question, but you may have another view on something, like we've tried this, or this was met with regulatory approval, and so we're really interested in those things. So if you can use your chat box, as Madison mentioned at the beginning of the meeting. Also, Hannah is standing by if you have any questions you want to dial in. And you know, and ask a question or give a comment. That's more than well received. So getting back to getting started on this topic, just a discussion on sink conditions, this really refers to, you know, how soluble or solubilizing the dissolution media is. We're somewhat limited by the traditional dissolution test. With a 1-liter vessel, we typically run about 900 milliliters in it for various reasons. That's just become the standard volume. I know a lot of the old BP references, British Pharmacopoeia had 1,000 mil volume capacity in many exercises. But for most, you know, a 900 mil volume is about the maximum people prefer to use. When we look at sink conditions, there's an important aspect that if we approach saturation, in other words, if a drug is saturated in a 900 mil volume, the label claim of that drug, you know, we have to do something to increase the solubility to a point where we should be about 3 times beyond the point of saturation for that API. And again, this is usually the maximum amount of the, you know, the active pharmaceutical ingredient that's contained in that dose. There are some chapters that have suggested 5 to 10 times has been suggested, but what we're saying is that if you're 3 times beyond the point of saturation, there's really no need to add a surfactant to get to 5 or 10 times. That's really not necessary, because at 3 times beyond the point of saturation, it's felt like dissolution is unencumbered. It is not suppressed in any way. There's an availability of media to, you know, absorb that drug product as it's dissolving. So higher sink levels are generally not an issue. There's no need to artificially decrease solubility just because you want to. Even if you thought that would be a good idea, you have to justify that. Just to give a couple of regulatory references to this, we find this in guidance for industry. This generally is you know, a window into FDA's thinking on any particular topic. One that's mentioned in the dissolution testing of immediately solid oral dosage forms. For water-insoluble or sparingly soluble drugs, use surfactants such as SLS, sodium lauryl sulfate, is recommended, and these come from several publications, but primarily Vinod Shah. The need for and the amount of surfactant, however, has to be justified. Again, out of another guidance for industry, this is on scale-up and post-approval change for modified release products that adequate sampling has to be performed, for instance, at 1 to 4 hours and every 2 hours thereafter until 80% of the drug form is released or an asymptote is obtained. Again, it says a surfactant may be used with appropriate justification to increase that solubilization. So we'll talk about what we mean by justification in a few minutes. For right now, it's just going to be that we know we have to do it. And Ken and Vivian, jump in anytime you want. And again, folks, if I say anything that's confusing or you'd like some more information on, you know, please don't hesitate.
Okay.
So solubility is mentioned in the new chapter. Not mentioned. It is the title of a new chapter, 1236. And what this chapter is really focusing on is the thermodynamic equilibrium. That is saturation. That's where a solute is uniformly mixed into a solvent, and it is at a state of equilibrium, which is equivalent to it being saturated. All right, so whenever we say thermodynamic equilibrium, saturated, those are basically the same. So solubility, you know, are generally stated in unit concentrations such as molality, mole fraction, mole ratio, weight volume, you know, weight. There's a number of different ways to look at this, but it's usually some type of weight volume that we, you know, very commonly use, especially on a test that you'll see for the shake flask method that we're going to mention in a moment. So dissolution is a non-equilibrium process of approaching the solubility limit at thermodynamic equilibrium, and this is a point where it's uniformly mixed, and the rate of dissolution will affect the time really affected to reach equilibrium. It will not affect the final equilibrium. So we're looking more, you know, when we're talking about thermodynamic equilibrium, we're not looking as much at rate, but more on extent. So dissolution is a process for really determining the rate and the extent of that amount of drug that's going into solution. So today, we're not as much focusing on the rate as we are the extent. As far as dissolution, we are trying to get a very accurate determination in the presence of excipients and so forth, the manufacturing techniques that go into controlling the delivery of drug as it dissolves. And there are a number of factors that it's not just what's in the media that's dissolving it, but there's quite a few properties of the dosage form itself and the API that will control or inhibit or enhance the solubility of this drug in a certain media. So the three things to basically look at here, and these are described in that chapter 1236, but we'll look at physicochemical properties of the material, the API, the properties and solubility of the media, and the control of solubility measurements. And this, you know, mentions them, and I'm not going to go into a particular detail on any of these, but just a high-level view of what we mean by physicochemical properties of the API. Of course, surface area and particle size are huge for allowing it to solubilize. In other words, large particles compared to a micronized or a powder, if you will, can have a tremendous impact on rate, the rate at which something goes in. Now, these do not necessarily have a big influence on extent. Like, you know, it may take it longer to go into solution, but eventually the drug will be in solution in a saturated state, so we can determine that concentration. Okay, but if it is a poorly soluble drug, control over these three areas, surface area, particle size, and the crystalline versus amorphous state of the API, will have a big influence on rate. So understanding something's poorly soluble is one thing, And then understanding what we can do to increase that physically is another.
Yeah, Brian, there's just one minor detail in that the particle size distribution is also important. Obviously the particle size, but the distribution of the particle size is sort of a minor detail, but you should be aware of that.
No, that's a good point. You're talking about if the API is many different sizes,
right,
or are you talking about the distribution of that API within a drug product? You're talking about just a whole lot of
the different sizes of. I mean, and there usually isn't just one, narrow particle size. Usually there is a distribution, and so sometimes that becomes important because you might have a particle size distribution that has a fairly high percentage of larger particle sizes than smaller, and so on and so forth.
That's a good point. I think that's all part of the big thrust into quality by design now as well, right?
Exactly. Exactly.
Yeah, to understand what they call that, a critical quality attribute. In this case, it would be like the distribution of multiple size particles across. And that has a huge impact on batch-to-batch variation. I mean, once this drug goes to manufacture, effectively you could have a drug that is going to fail some type of dissolution test because of it.
True.
Other things, moving on to the media, there's quite a few things that affect, the solubility that the media has for this drug in terms of its pH, polarity, surface tension, added surfactants. We are discussing about poorly soluble. The use of co-solvents, which is usually discouraged unless, there are products that are quite difficult to put in to solution with extra volume, even the addition of surfactants. So solvents may be a last resort that may need to be used. And then there are salts. Sometimes the API could be, maybe remanufactured or developed to provide, a way to make it more soluble. But buffer salts and things like that can be very, very helpful as well.
Brian, I'll just add one more thing back to I guess this might come under surface tension, but the osmolality and the viscosity, especially with injectables, is a very important aspect that you have to consider too.
Oh, this is true, yeah. And see, that's going to apply more toward these nano dispersions and micro dispersions because they themselves have certain surface energies that make them more or less soluble. Sometimes they actually are so small they try to clump all together, and it makes them very difficult to put in the solution.
And
sometimes that's
Go ahead.
No, but that's a great point. I'm glad you.
And also molarity. The molarity can affect the solubility. At times, people can vary the molarity of a media to increase or decrease the solubility.
No, that's true. That's very true. And I think a lot of those are mentioned in that chapter. Things that, avenues that you can take to, to increase the solubility of that drug. Of that drug in the media. And then, there's the solubility factors themselves where you're looking at control of solubility measurements. This is, doing a test and how to do that consistently to get an accurate picture of how, the solubility profile of this drug actually is. And this is going to be controlling temperature, of course, allowing enough time for this to go into solution, but, many things are kind of rate limited in terms of the final formulation, in terms of, we don't want this thing to be dissolving forever. But then, back to the testing, the agitation method is very critical as well. So we're going to spend a few minutes looking at solubility measurement, the things that affect that. So factors affecting solubility and measurements, come from the pH, the solubility of, you know, ionizable acids and bases are pH dependent. Salts and counterions, you know, may form salts which oppositely charge counterions, and I think this is some of the buffering that you were mentioning there. So the solubility of decreases as common ion, counterion increases. So this is called a common ion effect. Co-solvents. Because water is often a poor solvent, for some small molecules, but combining it with other solvents may, and again as a last resort, may be necessary to increase solubility, but that's usually when everything else has failed. I probably should have put that last, I guess. And then the discussion, the topic du jour, surfactants, and these really deal with some type of material that is, above the critical micelle concentration, CMC as it's called, and the number of micelles in a solution increases linear with the increase of a surfactant. But that is once you get above the CMC. And we're going to show you a chart in a little bit that's available in actually the 1092 chapter, the dissolution method development and validation chapter. A chart that shows some of these minimum, the CMC for these various surfactants. And I know mentioning micelles, but just a very brief, this is an aggregate of molecules in a colloidal solution. This is something that would be formed by, by detergents. So in other words, it's just a rate at which the surfactants are effective.
Brian, I see some questions. Two people have questions. Great. I don't know how to find them.
Yeah, go ahead. Just, do you want to read one out? And
I can go ahead and read them out if you guys want to answer a couple.
You want to go ahead? And I can't see that from my screen right now.
Yeah, I can't see the questions either, so go ahead and read them out.
Okay. Well, let's start with this first one. So what does it mean the asymptote is reached during dissolution?
The asymptote. In a dissolution profile, for something that was a sustained release product, you kind of see the dissolution rate going in a linear progression, a zero order release. But in any type of dissolution, the drug is eventually going to be all dissolved. And in a typical dissolution profile, which is nonlinear, it's completely, and you guys correct me if I'm wrong, but it is completely dependent on surface area. It's this controlling, how much is released at each time, because as particles become smaller and smaller until the point they're non-existent, the incremental rate of release diminishes to a point where, you're at 98% dissolved and it just stays that way. So if you kept sampling for another couple of hours, you wouldn't get any more because there's no more left to go in. So that's called an asymptote. It's when you've reached a plateau of release. And the next, right?
Well, I'll just add to that. And sometimes the asymptote is essentially when the dissolution profile plateaus, and it means asymptote because it's not necessarily getting to 100%. It's more like 90%, but it levels off. And this can happen sometimes when the matrix just won't let go of the API, and that some is just so tightly bound that it won't release.
Or you might see it with a coning problem as well.
Where drugs trapped underneath the cone in the bottom, And I think one of the biggest things, too, is like if you take a veterinary aspirin tablet and tried to put that in a 900 ml dissolution vessel, you'd probably reach an asymptote after about 20% dissolved, because it's saturated. It's not, you've approached saturation and the dissolution process has stopped. So in some indicators, but in any case, the asymptote is just where it's reached a plateau. Next question.
Thank you so much. Okay, next question. So about the particle size, what if it is nanosized? How do we perform dissolution in an effective manner since there will be a lot of variations in surface tension?
Vivian, you want to give that one a shot?
Could you repeat the question? That'll help. It's a little bit unclear what they're asking.
Of course. So considering this is going to be about particle size, they're asking what if it is nanosized? And then they also say, how do we perform dissolution in an effective manner since there will be a lot of variations in surface tension?
Let's see. Dissolution for nanoparticles is challenging. I think we're even going to devote another panel discussion in November on that.
Yeah, it might be best till then, almost, because that's a really involved question. So, while the question is right on, the answer to that is going to be lengthy, and I think it'll be best addressed. I appreciate the question because that it can add a facet to the discussion we have in November. But hopefully you can tune back in if we can push it off till then. That would be great.
One thing that would be really great is if you could post that question on the dissolution discussion group board itself. We can handle it there and answer it there since it's a little bit out of the scope of this talk.
Yeah. Thanks, Ken. Good suggestion.
All right, thank you. I will go ahead and I'll let the attendee know that redirect them to that web page where they can put the question there, but at this moment, there are no other questions. So we can go ahead and continue.
All right. So there are other things that, this actually is the prelude of the question that was just asked, I guess, but factors affecting solubility, there's a continuation of the things, the complexing agents, complexes with low solubility materials can enhance solubility. Surface area, goes into mentioning something I said a moment ago. Even though the surface area will not affect equilibrium solubility, it will have a huge effect on rate and how quickly equilibrium is reached. And as Vivian showed, if it's a wide distribution of surface area, of course, you can have a lot of I guess, sway in how fast it's going to release, which would not be a desirable, situation in the manufacture of pharmaceutical products. And then, as the question mentioned, surface energy for nanoparticles, when a particle size approaches that range, the nanoparticle range, the surface energy alone of the particle may increase its solubility. But again, we've seen a counter side to that where some nanoparticles, just because of their size, will begin to clump together, and it may decrease. It unfortunately may decrease its solubility just depending on the agitation. Now, how do you measure solubility? Well, I wish there, I could say there's some groundbreaking, procedure for determining, thermodynamic equilibrium solubility, but there's been a method that's been probably in use closer to 50 years, and is still probably the most reliable and commonly used, and this is called the shake flask method. I'm going to go over what some of the primary components are, and Ken's got a nice little follow-up to this on maybe some quick tests that you can do for solubility to look at the range of tests that you could do to narrow down the scope of that project. And this all relates to BCS as well. Classifying as a 1 and 3, which is highly soluble, or a 2 and 4, which are poorly soluble. So there needs to be a method that's used, and shake flask method is the most common. In this, what you're doing is starting off with a volume of liquid and adding an excess of solid drug to it. So it's just like adding a lot of sugar to water. You're just trying to see at what point it's just not going to hold anymore. And, you know, of course, at the end of a test, if you don't see any particles in that flask, then you don't have enough drug in there, because you need excess drug that's precipitated out on the bottom. But you want to do it in a practical sense. I'm saying I don't want half of this, you know, this solution to be, you know, consistent of particles in the bottom. We want to put in excess, but not a dramatic excess. So the final assay, after allowing this drug to dissolve over a period of time, it generally takes several days. You know, you are going to need to look at replicates, usually N equals 3 for each level, to determine that amount of drug that's in solution. You'll see the various buffers used, and I'll show you some of those pH buffers in a moment that are used. These are USP buffer solutions at concentrations in pH that are mentioned in the buffer section of USP. But typically on the flow chart here, you know, you weigh the sample, add that to it. You do need to keep the pH control and measure. Now, there's a lot of controversy on whether you adjust or whether you allow the pH to change on its own. I'd be interested in the panel's views on this. But shaking usually commences in these vessels, or not vessels, but generally a stoppered flask, for 24 hours at 37 degrees, and that temperature needs to be controlled very tightly. So the pH is on target. If it's not, this is where some people feel like it could be adjusted. Some feel that you should just make a note of it, to make note of the buffering capacity, that the API is contributing. If it's on target, fine. You can dilute. Of course, these are going to be near saturation, so you're going to need to dilute them down to get them in an analytical working range. You're going to have to make a standard that's in a reasonable range for analysis. And it's highly recommended that you do HPLC analysis. And this is so we can get an idea of, you know, that product, if there's degradation processes going on, or other issues that may be affecting that solubility. So the analysis of the solution, you know, it could be done by UV, but again, HPLC is preferred, and because of drug-related impurities. The solubility results, the pH of the solution should be recorded when the sample's withdrawn. Again, I've heard both ways. Some adjust it, some don't. I know when we used to do it, we did not adjust it, but just mentioned it so we could see the buffering capacity. The excess solid should be analyzed in the bottom to see that it has not changed. We don't want to find out that there's none of the original drug and all of that product in the bottom is just, you know, a degradation compound or something. We also need to report the solubility at the final time point, consistent with the results. And what you're looking for is the final two results should match. So in other words, as this is approaching saturation, this process is slowing down. It's going to take maybe an extra day or two to get that last bit into solution to truly understand the thermodynamic equilibrium. And the way I relate this is like drying something to a constant weight. You just want to make sure your final two solubility measurements are the same.
Now, Dr. Brian, yeah, you do have a question, but the other thing is I wanted to add, you know, in normal method development, when you're coming up with a media, you know, you are measuring whether the pH changes after the dissolution test is done. So it is important to at least make a note of this, and you wouldn't choose if you have a choice. I mean, sometimes you're just finding out the dissolution for regulatory purposes in a certain pH. But, you know, ideally you would not have a dissolution media where the pH did change over time. And like I said, you have a question there somewhere.
Yeah, I just want to follow up with that. Yeah, truly water, you can definitely have huge issues, but FDA discourages it for that exact reason. There's no buffering capacity. So the pH buffers that you'll see in USP, they're fairly rugged in most cases, and I agree with you. You know, I know when we did it, we did not adjust the pH. We made note of it to see if that was something that could, you know, it could cause some issues, or maybe we could modify our media to be a stronger buffer or something. But generally, that it is very important to note. The question, is there a question?
Yeah, the question is, how can we determine the rate of solubility for API?
The rate of solubility. Well, you know, that could simply be done, but you're not going to want to do it in excess. I would say, you know, even doing a solubility measuring test, if you took a lot of samples out of it as it was in its early stages, you could maybe get an idea of rate. But
I mean, to me, this reads
is
like
a particulate test. You can do it in a regular dissolution vessel and add the maximum dosage strength of a drug and put it in a vessel to look at, you know, how fast that's going into solution. But generally, the excipients and the formulation are going to be done. You also have the intrinsic dissolution test, which is, you know, basically going to give you, with a constant surface area, you're going to get a linear release of drug. And that's probably the most prevalent test.
Yeah, that's what I was going to say. There's one more question in the chat box as well, but it doesn't really pertain directly to this conversation. It's about apparatus 4 getting into a specific flow rate and method. I think that one would be better suited for either a later talk or posting that directly on the dissolution discussion group.
Yeah, I would put it on the DDG bulletin board, because with an hour here, we may not have enough, we wouldn't probably have enough time to go into it. I appreciate the question, though, and this is the kind of thing I really like to hear, because it makes us think about peripheral areas, of course, when we're talking about solubility here. So thanks for the question, and we'll follow up with how you can post these pretty easy on DDG. In talking about solubility, you know, it's even regulatory agencies, they're in, I'd say, common agreement, but as far as the specifics, you may see, you know, I think EMEA is the way a lot of thinking was here. You typically used about, you know, 3 or 4 different points to prove solubility, demonstrating that range from pH 1.2 on up through 6.8, with 4.5 being a midpoint. Now, we see FDA's thinking, you know, you should demonstrate at least 5 buffers, and this is all centering around the pKa. In other words, you typically start off with a profile of pH around 1 and finish around 7.5, which I think is good, because that actually is encountered, and for a weekly basic drug, you may see some real issues there. But this really does center around the pKa and then plus or minus 1 pKa. So you're really trying to center that around, you know, where half of it's ionized and the other half is not. So that might be a little bit more effective. But you should have a minimum of 3 replicates. And if you are, you know, looking for approval with either of these regulatory agencies, just be aware that there might be some slight differences. Even in this world of harmonization, not everything is appropriately harmonized.
So, Brian, we do have 2 more questions, it looks like.
Okay.
If you'd like to get to those now. The first one reads, how much is the volume of buffer used to establish the saturation point in the method of Shack Flash?
What was that last?
In the method of Shack Flash?
Shake Flash. Shake Flash. Sorry.
Yeah, shake. Yeah, it's, you know, I hate to say it's a monetary issue. Ken, correct me if I'm wrong. I work with new products that the initial API was so expensive that it's like they give you a gram and say, hey, this has to last you for a month. Ken, you ever experience that, Vivian?
Oh, definitely.
So it's like, I hate to say it like this, but it's whatever you can get away with. You might we run these tests in like 50 ml flasks and things, which is extremely difficult. And
yeah, I mean, I think the important thing to consider when you're looking at the minimum volume is what the accuracy of your analytical balance is. As long as you've got confidence there that your volume and your weight are going to be accurate enough to do the test, then by all means you can go lower.
Yeah. In a generic instance, there's usually an abundance of this. This is not an issue, and if you can go 500 milliliters in each flask, that's great. But just beware. Sometimes there's some I hate to say physical constraints, but there are monetary constraints in some of this. But and just the availability of it, it's just not there. You know, for a generic sense, it's much easier, but it's really dictated by, you know, you are trying to put a certain amount of drug in solution and you do need an excess. So volume is really not mentioned in this. I don't remember in chapter 1236. Do you, Vivian? I don't think it comes up and says you got to use a 250 ml flask or 500 or something.
Yeah, I think it more comes with the BCS classification. They give you, you know, 250 mils of your highest dose.
Okay.
That's all I know.
No, that's a good point. That's a good point, because most of the BCS is in terms of a maximum dose going into 250, and maybe that carries over into the solubility to, you know, shake flask method as well. That's a good question.
The shake flask, excuse me, is determining, you know, saturation and solubility from one standpoint. With the BCS, you're just seeing, are you meeting a certain standard of solubility? So it's a little different concept for the two.
Okay. And the other question is, we've already answered it. It says, if the shake flask method, it requires a lot of API, how do we tackle this? And this just dovetails with the volume, so we can move on.
It will, and you know, the initial stages of drug development, it consumes a lot of API. You've got to get the intrinsic rate. I mean, to understand the rate that the drug itself is going in is one of the other questions raised. That can take, you know, grams of API and more, depending on how many tests you run. But the solubility, I think, consumes way more. Okay, so the solutions to solubility issues. Once we determine that we have, you know, a poorly soluble drug, according to BCS, it falls into a 2 and a 4. And you got to remember, there are some drugs that fall into the poorly soluble category because they failed one of those pH where it wasn't soluble. You take a drug like ibuprofen, it's quite soluble in pH 1.2 and 4.5, but at 6.8 is poorly soluble because it's a weakly basic drug. And I think they call that a class 2B or something like that. Is that right, Vivian? And, you know, some types of drugs like that are going to fall into a class 2 solubility category.
Right.
So there's things to work with there. But anyway, surfactants, you know, we're going to focus the discussion now, shift it a little bit toward the solutions, I mean, like the answers to solubility issues. So some of the best things are to evaluate different surfactants at the time. There are quite a few, and we're going to go over these in a little more detail in a minute. You'll see constantly mentioned, probably the most common is sodium lauryl sulfate, SDS, or its identical name, sodium didecyl sulfate, SDS. Tween, very often used, CTAB, and rarely bile salts. These are naturally occurring surfactants. And by the way, there are naturally occurring surfactants in the GI tract in the terms of bile salts. So it's probably more of a biorelevant approach, but definitely not a preferable one. So when we perform these studies, you're going to create 4 or 5 different media depending on the issue. Again, we're suggesting 250, although there's no, that's basically because of the BCS, as Vivian had mentioned. You're going to add a different surfactant to each, add API equivalent to the dosage strength, and put it in an orbital shaker. Ken, these are some of the ones that you were going to discuss, I think, right?
Yeah. So this is just a quick screening to see what some good potential medias would be that would meet sync conditions with your API. So this is a little bit quicker and easier than just doing the straight solubility study. So I've recommended creating basically a matrix of different media combinations. So you can create 4 or 5 different medias across the pH from, say, 1.1, 1.2, all the way up to pH 7.5. Add some different surfactants to each one of those to create the matrix. Add your API equivalent to the dosage strength, as Brian said. The thing that's nice about using 250 or maybe 300 mils is that by adding the API strength to this 250 mils or 300, if you end up being soluble in that volume, then you know you've met sync condition because sync condition will be 3 times that, so you'll fit within, say, a 750 mil, 900 mil dissolution volume. So once you've got your API in the various flasks, you can put that on whatever sort of shaker or agitation device you want to use, and just simply do a visual check and see what has and hasn't dissolved. And if you want to go to the next slide, Brian.
Okay. I was just going to make one note on the mixing of it, that has to be temperature controlled, or suggested that it's put in some type of hot box or controlled environment chamber where it's maintained.
And so coming out of that solubility screen, you can kind of get a feel for what the best combinations are for surfactants or perhaps no surfactants in pHs, and just get a general idea before we get to the dissolution tester on what may or may not work. One thing I do want to note about SLS is that if you are using SLS, that is not going to go well with a potassium phosphate buffer. You always want to use a sodium phosphate buffer because you'll have that SLS crash out of solution when it's cooling in, say, your HPLC vials or test tubes after you collect the sample. Next slide, Brian.
Mm-hmm.
And then once you have a good idea of potential surfactants and some media combinations, in the previous slide I had everything at 0.5% of different surfactants, you can go backwards from that point and see what's the minimum amount of surfactant that we might need to still achieve sync conditions under that media combination. And so anyway, that's just a pretty quick and dirty test that I'll recommend to find some good combinations of medias and surfactants with your API of choice.
Oh, that's great. Thanks, Ken. And folks, remember that these are recorded, so if, we don't want you to have to take a lot of notes here, just to be thinking, and you can come back to this and reference it by coming to the Agilent community and picking these up, or the dissolution discussion group page. Okay.
There is a question out there, I see.
Ken, can you read that?
Yeah, it says if pH equals pKa, we called 50% drug in ionized form and 50% of drug is unionized. When there are 3 different pKa values mentioned, which value should we refer?
Three different pKa for
yeah,
one.
I mean, that wouldn't be very typical, right, to have 3 different pKas? But I mean,
I would think it'd be fairly atypical. Yeah. Ken, you have much experience with that? You may, at that point.
Not too much, no.
Yeah, at that point, if we're looking at 5 and you have 3 pKa or something in one chemical entity,
well,
let's just say
do them
2,
all
maybe.
±1. I bet there'd be overlap.
Yeah, there probably would be. So I'm saying you probably run the 3 different, the beginning and end, like the pH 1 and 7.5, and then run the 3 pKa, and then you might have to have 7, total here, because it -1 below the lowest and +1 above the highest, I guess.
Right.
So
bracket, maybe.
Yeah. That's a good question. So, I guess we've been kind of keeping up with the questions and so forth. I want to hop out to Hannah and see if anybody's dangling on the line out there anywhere. The chat box is a very efficient way to do this, but if you'd like to tune in that way, let us know.
There is one other question in chat. What is the allowable pH change for before and after dissolution experiment? I'm not sure I understand that.
Allowable pH.
What's the amount of drift of pH that's okay during the dissolution run?
You mean when they're doing a solubility study? Like when
I think just during a dissolution in general, or in a solubility study.
Well, you have the specifications for, plus or minus 0.05, I think, pH for controlling the pH. I would look at that as a possible guide, but I don't think there is one specifically.
Yeah, I know that when you prepare a buffer, that's the 0.05 is what your accuracy of that buffer should be. Now, about the capacity and influence that a drug has on that, I don't have an answer off the top of my head. It might be buried in the chapter, the solubility chapter, but I don't know. Great question. This is an effective program where we can answer some things and can't answer others. So, again, this might be a good question for the DDG, the bulletin board, because there's a lot of experts out there that rely, heavily on these tests and do them every day, and they may have some practical answers. So, maybe I just default to see if the poster of that question wouldn't mind putting that on the DDG. And just say you were here, and that way we'll get some attention to it and maybe try to research it on our end a little bit better. Okay, so, we've mentioned BCS several times, and just to give everybody a ground state for this, we're looking at the right side of this matrix. These are the low solubility drugs. Solubility is one thing. This is the point at which a drug is available for permeation, available for absorption. But that can have a big effect on permeability depending on how fast it goes into solution. If it's not all going into solution for a long period of time, you're missing a window where a lot of this drug could permeate and actually do something. So they are hand in hand, but for the sake of discussion today, we're just looking for the solubility of the drug. Looking at Remington's, just, to give you an idea of solubility classes, something that is less than one, to take a gram of solute and put it in 1 ml, if it goes into solution, of course, that's extremely soluble. But to give you an idea of a sparingly soluble drug, anywhere between 30 and 100 mils to put that drug's product into solution is going to be, still on the solubility side. But, we start to get slightly soluble, very slightly soluble, and practically insoluble. This is a lot of the areas that we're dealing with today, as far as being very poorly soluble. Factors, we mentioned things that you know, affect the solubility of the drug or the extent of drug. Of course, the API selection, the media volume, the saturation, solubility in terms of pH, presence of surfactants, and non-aqueous solvents, which I'm using the word non-aqueous here to describe organics. This is typically anything from an alcohol to, you know, to propanol or octanol, anything like this that would not typically be what we consider aqueous media. But this all has to be relative to sink conditions as well. Ensure that highest dosage strength is soluble in 250 mils or less of those different medias that we've been discussing so far. API, again, it's a little bit more. We're talking about the selection. API has an effect on both rate and extent. Again, rate comes up when we deal with things like particle size and so forth. The crystalline versus amorphous state of a product has a huge impact, with crystalline forms being, because of their high energy of bonding and double bonding, it makes it much more difficult to put into solution than something in more of an amorphous state. We have to be careful with polymorphs. This really comes up during an intrinsic study where you're using a pretty significant amount of pressure to make a compact or a pellet to determine the rate that this drug's going into solution, but we don't see it exist that much in terms of solubility testing. And then, of course, there's complexation and salt formation as well. Media volume.
Just one note on that last slide, Brian.
Sure,
I do want to recommend to everyone, if you're dealing with an API supplier that you haven't worked with before or a new API, I always recommend doing some pretty extensive checks on that to make sure that the API is what the certificate that comes with it says it is. A lot of my customers have had issues with bad incoming API or it being very variable from lot to lot. So just wanted to point that out.
No, a really good point. Probably the most long-standing way of dealing with a poorly soluble drug is just increasing the volume. There's only so much that surfactants can do, and I don't know how many out there have tested veterinary products or bolus products, but these have a huge impact on, you know, the solubility of this maximum strength. And, you know, when you look, like, again, at some aspirin tablets for bovine and equine species, I mean, these things are several inches long, and they have a tremendous amount of drug. And you know, a 2-liter vessel shown on the left there may not be enough. Sorry, that's a 4-liter vessel on the left, a 2-liter in the middle, and a 1-liter vessel on the far right. So the media has long been a common sense way to do it, but it's not always practical because you have to have a very special dissolution apparatus or a modification of that apparatus just to be able to handle, you know, so much volume. The saturation solubility pH, if that API is ionizable, solubility may increase by a change in pH. At pH approaching the pKa, more of the API is ionized, the solubility increases. So, you know, these are just some things that can control that saturation through pH. Surfactants, you know, they're probably the most go-to, I guess, of solutions, but again, recognize that typically 3 to 1 is what you're shooting for. Now, does that mean you have to have 3? I'm going to say right now that FDA has accepted product that may be slightly below that, but they've been justified to control that release where it does not, you know, typically suppress the rate of solution in terms of its extent is what you'd have to, I'm sorry, in terms of its rate before you reach that amount where it's saturated. But you'd have to have a bit more justification there. But for solubility enhancement, surfactant concentration above that micelle limit will depend on the surfactant itself and also the ionic strength of the media. And of course, there's various surfactants that are going to be, basically able to pair with that drug as well. Some are more effective than others. Excess surfactants can cause a drop in discrimination. This is the primary reason that surfactant levels have to be justified. So in other words, if 0.2% sodium lauryl sulfate will do the trick, and we throw in 0.5% or more, we may actually cause the release to be fast enough where we lose discrimination or the ability to tell a good batch from a bad one. It's just, it's overriding the effect of looking at the true, the product going into solution, but forcing it to be faster, which will, not allow us to have the discrimination that we have in our test that we should have. So when we look at, there's a good statement that comes in SUPAC modified release. This is, again, a FDA guidance, and it was put out a long time ago, but it is still very helpful for looking, and we'll just read through this. Where the concentration of surfactant used for the test should be justified, typically the lowest concentration required to achieve acceptable dissolution should be used. SDS concentration range of 0.1 to 3 or higher has been used. In unbuffered water, however, SDS at concentration below 0.23 behaves more as a wetting agent. And that's generally because I'm below that critical micelle concentration. If the SDS at a previously approved concentration does not yield at least 85% in 60 minutes or interacts with the active, other surfactants listed on the FDA website should be examined. So there are, basically this is a hand-pick thing. There's really not a list, but this directs you to the FDA dissolution, what am I trying to say here? This directs you to the FDA dissolution method database, okay? So you have to kind of cherry pick which ones have surfactants and what those are. A much more concise term, chart, I think, has been put into the USP in Chapter 1092 on method development and validation. Now it comes to light where the ionization of the drug can be paired with maybe a more appropriate surfactant. And many times we're looking at anionic surfactants, sodium dodecyl sulfate or sodium lauryl sulfate. And again, that critical micelle level and percent weight volume is 0.23%. Or greater that we need to be to have an effect on that. So this is showing the CMC, the critical micelle level, for each of these different surfactants. I think the other one's probably the most prevalent, and you guys let me know what you think, but generally, I've used CTAB, polysorbate 80, and yeah, I have had to have used Tritenex as well, but that probably comprises about 98% of what I've had to use. Any thoughts on these?
There's a question out there, Ryan, I see.
Okay, Ken, can you read that one? Or Vivian?
It looks like it's a response about the multiple pKa's from one of the other attendees. It says, multiple pKa's arise due to multiple ionizable groups on the drug. A good example of this is an amino acid. I would guess that your selection of pH or pHs should depend on what the active form or forms of the API is or are.
Excellent. This is why we have experts from around the world come in here and help us through these topics. So, and again, this is a discussion. It's that's valuable input, and and that's what we're looking for on the discussion group. Thanks very much. So just a word on organic solvents here. I mentioned volume, we mentioned surfactants, but organic solvents, again, are generally unconventional and used as a last resort. However, this has not prohibited their use. Proof above all other strategies failing has to be provided. So what we call this is more of a trail of tears approach. You have to exhaust yourself on all the, the volume and surfactant and, media, even how we handle the API. Are there salt forms of the API that would be better? Things like that. So when everything has been exhausted, and if this is the form we have to deal with, then of course the use of organic solvents or non-aqueous materials may be required. But again, significant justification needs to be given for that as well, because like surfactants, too much of it will you'll lose discrimination in the test. And for many drug products, any amount of alcohol can really affect those discrimination capabilities of the test. So we've run about 7 minutes over so far. We have, I think, kept up fairly well with the questions and suggestions that the folks tuning in have provided. And this is more of a general wrap-up and discussion. First, Vivian and Ken, what do we miss here? What did it look like we covered this?
Yeah, I have a couple of notes that I was thinking. One, in your actual validation, the concentration of surfactants should be under the robustness evaluation, meaning that you should use different percentage of, if you have like say 1% surfactant, you should go maybe 1.2 or 0.8%, just to show that the method is robust to small changes. That was one thing I wanted to mention. And then the other was that to get discrimination, sometimes you need to go below sink conditions. And this is, remember, sink conditions are not mandatory, they're just desirable. Of course, the ultimate goal of a dissolution test is to show discriminatory power, and if you need to actually go below sink to show that, that is okay. Those are my two notes that I had.
No, excellent. That's two great refinements right there. Ken, any thoughts?
No, I think I'm good.
All right. I like your quick and dirty solubility determination. You probably that can save a lot of time. And now I should mention with that there are what are they called? In the 1, 2, 3, 6 chapter, there are other techniques that may be used to judge apparent solubility. And there's some very rapid screening, things that can be used in with DMSO titrations and some other things that sound, hectic, but it's like they may be able to provide more results, like a high throughput type of screening on solubility. So you can, some of those allow you to narrow your choices. You see, you should still do the thermodynamic equilibrium with the shake flask method is what I'm suggesting. Maybe not everybody, but at least with some of those other approaches, you might be able to narrow it down pretty quick. As far as the help that I've had today with our panelists, we just pulled a lot of this material from some different publications. Some of these came out of Dissolution Technologies from long ago. Brian Rohrs used to be a big contributor to this, and I think I grabbed a couple of things that he had written on there. And then, of course, there's various guidance for industry from FDA that have been very helpful, including SUPAC, and then, of course, the USP chapters 711, 1236, 1092, which can be quite useful. Okay? So, wrapping up here, is there any questions lingering out there?
And for those of you on the phone, it is *1.
Thank you, Hannah. There are currently no other questions in the chat or Q&A.
Okay. Well, I think we've got enough to wrap this up. So I would really like to thank, first of all, the panelists for their participation today, and also everyone out there that is dialed in. We hope this has been helpful to you, and if you find it that way, we hope you return for future sessions on this. And again, we appreciate your input in terms of what the topics are. Our next topic for our meeting is on micro and nanoparticles. It may not be, for everyone, but, as, we develop methods for dissolution and drug release, new products come along every day, and this is getting much more of a common delivery, maybe injectables and things that use some of these micro and nanospheres that require dissolution. And thinking through these is what we're going to do in our next meeting. But we do look for your suggestions on hot topics, things that are changing, recent guidance, things like that. So if there's a topic, look through the list first to see what we've done, and if there's something that, is generating an interest that would be helpful for others, please let us know. And you can let us know in suggestions on the DDG site. It's in blue right there, so it's not too hard to remember, dissolution.com. And you can get to that welcome page, and it shows you when these quarterly meetings are, and then you can make a quick jump over to the bulletin board as well to see what's going on there and provide input to others. Remember, this is a two-way street here. It's not just questions, but we look for help and get a lot of help on this page from all over the world on how to accomplish handling different issues. So these are held quarterly, 10:30 to 11:30 Eastern U.S. time, so please consult that site for any future sessions. And with that, I want to again thank our panelists. Thank you to all those that called in for your comments and participation. So, Madison, I'm going to turn it back over to you, and thanks again to Ken and Vivian for joining me today.
All righty. So it appears we have reached the conclusion of our event. So please join me in thanking the Dissolution Discussion Group for their quarterly meeting. I do want to remind everyone that I will be sending a recording of today's meeting as well as information to register for the next event in November within the next 24 hours. I will be leaving the session open for a few more minutes to receive any feedback or additional questions, but we are now going to close the audio line. Hannah, one more time, is there anybody in the phone queue?
No questions, thank you.
All right, thank you. So thank you once again for attending. And on behalf of Agilent Technologies, we wish everyone a great rest of your day.